In this presentation, we delve into pilot data that was collected to assess the effectiveness of a neurostimulation technique called transcranial direct current stimulation applied to the dorsolateral prefrontal cortex in an attempt to improve reasoning, reflective processing, and analytical thinking on a range of judgment decision-making tasks. I'm Michael Lundy. I'm a third-year PhD student at the Krosik Reasoning Lab located at the Center for Brain Health, affiliated with the University of Texas at Dallas School of Behavioral and Brain Sciences. And the inspiration behind this study was a publication from 2019, so relatively recent, in which Edgecombe and colleagues wanted to assess the effectiveness of this tDCS protocol in promoting reasoning performance. And one of the tasks they selected was the cognitive reflection test, or CRT. And what they found is in their between subjects design that those in the right DLPFC condition exhibited a marked improvement in performance on this task in contrast to those in the left DLPFC and sham conditions. This attests to an underlying asymmetry that might be at work with respect to information processing that takes place in the DLPFC. Our lab group was quite struck by this finding and wanted to follow up. First of all, to see whether or not we could replicate the CRT effect in our study, but also extend it into other behavioral domains, other judgment decision-making tasks, to see whether, if indeed reflective processing is being promoted by this stimulation condition, it should also apply in other task contexts. So starting with our design, we went with within subjects, crossover, sham-controlled paradigm, in an attempt to maximize statistical power from a relatively modest sample size of 9 participants. Starting with the CRT, we did not see a statistically significant improvement in performance by the right DLPFC condition in comparison to sham and left DLPFC. However, the left DLPFC condition exhibited a significant decrement in performance in this task, suggesting that this stimulation condition might have promoted impulsiveness or defaulting to intuitive judgment. Now, moving on to the next task, we presented a financial risk framing task to participants. Following the framing effect paradigm, financial decisions options are presented to participants in which there's a loss frame and a gain frame. And the information is equivalent in each context. It's just that what is emphasized is what differs in each context, and that can drive inconsistency in decision making. But our hypothesis was that if DLPFC stimulation proves reflective processing, that should reduce susceptibility to the framing effect. And that is what we found. The right DLPFC condition promoted resistance to the framing effect in comparison to sham and left DLPFC conditions. And lastly, we have a visual stop signal task, which was an attempt to measure whether or not inhibitory control might be a basic mechanism that's driving reflective processing. So in this relatively simple task structure, participants would press the left arrow when presented with a square, a right arrow when presented with a triangle, and preponderance of the task trial items were of these sorts. But on 20% of the trial items, a stop signal would appear at varying latencies, and it can be quite challenging to inhibit a prepotent motor response on this task. It seems suitable to that objective. However, what we found is that performance was roughly equivalent across the stimulation conditions. One caveat that must be brought up is that this sample size is relatively small, it being a pilot study. However, with the framing effect, framing task finding, we feel confident about moving forward to a full phase study, which will be improving our sample size, but also looking at basic neurophysiological mechanisms that might be driving the behavioral effect. In particular, we're interested in the locus coeruleus norepinephrine system because it's so tightly coupled to attentional control, vigilance, and inhibition. So we'll be collecting event-related potential, or ERP data, from the visual stop signal task, looking specifically at the P300 to see whether or not amplitude and latency of this ERP changes as a result of stimulation exposure. But we'll also be collecting alpha amylase salivary samples from pre and post stimulation and comparing those levels, because this particular enzyme is a reliable biomarker which is coupled to norepinephrine activity in the central nervous system. So we're very excited about presenting those findings in the very near future. And appreciate your time and attention in listening to this presentation, and feel free to reach out to our lab if you have any questions.